Hello, and welcome to The Space Above Us, Episode 3, Project Mercury Flight 1, Freedom 7, An American in Space. This is it. May 5th, 1961. America's first foray into human spaceflight. Later missions would go further and stay longer, but this is where it all began. Mercury Redstone 3, with its capsule dubbed Freedom 7, was the first manned flight in Project Mercury, which was established with the goal of launching a human into orbit and then safely recovering him. This first flight was to be a suborbital mission, meaning it would fly in space but not enter into orbit. At the risk of getting sidetracked right at the start of this podcast, allow me a minute to explain the difference and exactly how orbit works. Many aspects of spaceflight are counterintuitive, and this certainly includes orbit. From the perspective of a spectator on the ground, rockets launch vertically and then fly away into the sky. Given that everyone knows that space is high above the surface of the Earth, it is understandable that many people believe the rocket simply flies straight up away from the Earth until it reaches space. This is especially easy to believe when combined with the widespread understanding that there is no gravity in space, which is of course not quite accurate. It paints a picture of the rocket climbing a steep hill, and once it reaches the top, there is nothing pulling it back down, and it can remain there indefinitely. In reality, this is not at all how spaceflight works. If a rocket were to fly straight up into space, it would not be there long before falling straight back down again, assuming it didn't fly so fast as to escape the Earth entirely. In fact, an astronaut attempting to achieve orbit needs to fly sideways with respect to the Earth. To use a classic analogy for how this works, imagine a cannon on top of a very tall mountain. Fire the cannon and the ball flies out for a distance and then lands further down the mountain. But what if you fired it faster? Well, it would land further away. If you kept firing faster and faster, you would eventually start to notice something a little unexpected. The cannonball would travel so far horizontally that by the time it fell down to the ground, it may be over the horizon from where it started. The Earth had curved away underneath it. So, what would happen if you fired the cannonball so fast that the rate at which the Earth curved away underneath it was the same as the rate the ball was falling? For every meter the ball fell towards Earth, it would fly horizontally far enough that the Earth had curved away another meter. This ball would fall forever, or until it hit the back of the cannon, so watch out, and would be in what's called orbit. An object in orbit is simply falling towards Earth and continuously missing it. So it's not vertical speed that's required, it's horizontal speed, and a lot of it. So why do rockets even bother going straight up at all? The answer is that they need to get out of our thick atmosphere in order to achieve and maintain the staggering speeds required to stay in orbit. Objects in low Earth orbit travel at around 17,500 miles per hour. If a vehicle tried to travel that fast at sea level, it wouldn't remain a vehicle for very long. This brings us back to Freedom 7. While the eventual orbital Mercury flight would achieve enough horizontal velocity, at a sufficient altitude to maintain it, to orbit the Earth, Freedom 7 would be more like the cannonball that flew a little over the horizon before landing back on solid ground. The objectives for the Freedom 7 mission were to fly a pilot into space, ensure the pilot was capable of operating effectively in space, and test a number of subsystems during their brief time before re-entry. There were many questions to answer, including, could a human even stay conscious in space? Would they look out the window and feel so disconnected from the Earth that they would become insane? Would the various attitude control systems on the spacecraft operate as intended? Would the heat shield adequately protect the capsule during the rigors of re-entry? Freedom 7 is often overlooked in favor of the first orbital Mercury mission piloted by John Glenn 2 flights later, but it was instrumental in answering many of these questions. These days, it's easy to forget just how little was known about the space environment. At the time of this flight, the grand total of human spaceflight time was about 90 minutes accrued by Yuri Gagarin during his flight on Vostok 1. And while some details about the mission were known, the Soviets were not inclined to share a lot of information about what Gagarin encountered. Speaking of Gagarin, while this is a podcast about NASA history, I would be remiss if I didn't at least mention the flight of Vostok 1. On April 12, 1961, Yuri Gagarin became the first human in space when his Vostok 1 capsule was launched into orbit around the Earth. He completed one orbit while the capsule was under fully automatic control. After his single orbit, Gagarin endured re-entry before bailing out of his capsule in order to land under a personal parachute as planned. The Soviet flight was an immense accomplishment that came as a blow to many Americans who were hoping Project Mercury would ensure an astronaut, not a cosmonaut, was first in space. Yes, there is no doubting that Yuri Gagarin was the first human in space and will be known throughout all of history for his flight. But I can't help but point out two facts. First, Gagarin did not land with his capsule, so I think it could be argued that Alan Shepard piloted the first complete spaceflight. And secondly, there was a key word in that previous sentence: piloted. Yuri Gagarin had no control over his capsule. In fact, the controls were locked behind a panel that required a code to open. The code was on board in an envelope in case of emergency, and he was eventually told it, but this is a far different flight from those under the command of the Mercury astronauts. Shepard, as you will hear, manually commanded his spacecraft through much of the flight, putting his years of training to good use. So good job, Yuri Gagarin, and all those in the Soviet space program. But maybe an asterisk is in order in some of the history books. Anyway, like I said, this is a NASA history podcast, so let's get to it. The mission called for a Mercury capsule to be launched atop a Redstone rocket from Cape Canaveral. It would fly east over the ocean to a planned range of 290 miles, while achieving a maximum altitude of 115 miles. The flight was expected to take about 15 minutes. The capsule was dubbed Freedom 7, with the 7 being a nod to the original 7 Mercury astronauts, and perhaps to the fact that this particular capsule was capsule number 7, and this particular booster was booster number 7, by its pilot Alan Shepard, thus starting a tradition of the astronauts naming their vehicles. The public had known for a number of months that the pilot, and thus the first American in space, would be either Alan Shepard, Gus Grissom, or John Glenn, but NASA did not reveal the final choice until just prior to the flight, in case a last-minute switch was required. John Glenn served as the primary backup for this mission. Alan Shepard was a 38-year-old Navy test pilot who had joined Project Mercury, along with the rest of the so-called Mercury 7, back in 1959. I don't want to get too far ahead of myself, but it's worth noting that while Shepard's only mission in Project Mercury would last just over 15 minutes, he would go on to be the only one of the Mercury 7 to set foot on the moon as commander of Apollo 14 10 years later. With more than 8,000 hours of flying time, including tours aboard aircraft carriers, Shepard was among the best pilots the United States had to offer and was both qualified and eager to pilot the mission. Shepard was awoken early in the morning, just after midnight, on May 5th for another launch attempt. The previous launch attempts were scrubbed due to poor weather. Shepard started his day with an enviable breakfast of steak, eggs, toast, coffee, and orange juice. After donning his silvery pressure suit and returning to the pad, he left the cool early Florida morning behind and stepped into his spacecraft. It was 5:15 a.m. The launch was scheduled for 7:20 a.m., and the countdown had already been underway since 8:30 p.m. the night before. The NASA rocket I grew up with, and the one we would become very familiar with later, was the Space Shuttle, a gleaming white spaceplane the size of a passenger jet, mounted to the side of a massive orange fuel tank over half the length of a football field, and 2 of the largest solid-fueled rockets in history. I would watch 7 astronauts climb aboard the cockpit with room to spare. The Mercury launches were a bit different. The entire stack of Redstone rocket, Mercury spacecraft, and escape tower topped out at about 83 feet, just a little over half the height of the orange external tank on the Space Shuttle. The launch site had no large permanent service structure, but was instead serviced by a small mobile gantry. The spacecraft, interchangeably referred to as a capsule, was a mere 6 feet 2.5 inches in diameter and 6 feet 10 inches tall. The Mercury astronauts used to joke that you didn't get in the spacecraft, you put it on. The vehicle was conical in shape, with a cylindrical portion near the top that contained the parachutes, antenna, and other equipment. The exterior was dark and ruffled in appearance due to numerous heat-absorbing corrugated shingles that covered the surface forward of the heat shield. Each vehicle is different from the others, with their own customizations and quirks that changed from spacecraft to spacecraft as lessons were learned and mission objectives updated. I love looking at close-up photographs of the Mercury cockpits. You can pick out great details like the slightly worn hand controller, bundles of wires routed around control panels, handwritten labels and notes. The vehicle feels handmade, because it is. As astronaut Shepard settled into his cockpit, the launch was again delayed due to overcast conditions, which would prevent vital photography of this first mission. There were also a number of minor technical problems that had to be solved. The delays eventually extended to nearly 3 hours. While I'm sure the delays were frustrating at the time, I've always been a little grateful for them, since they led to 3 famous moments that reveal much about Shepard's personality. The first was what's sometimes known as Shepard's Prayer, which the pilot said to himself shortly before launch, and to keep this a family-friendly podcast, I will quote it as, quote, "Don't mess up, Shepard." Second was an amusing, but somewhat serious situation where Shepard reported the need to urinate. The planned mission duration was only 15 minutes, so no mechanisms were on board to accommodate this basic human need. Ground control told the pilot it was not possible since it would be too time-consuming to return the gantry to the spacecraft and extract the pilot. A frustrated Shepard reported he would just relieve himself in his spacesuit, leading to alarm among the engineers that America's first astronaut was about to electrocute himself in his own pee. A compromise was struck when the electrodes in the suit were powered off long enough for Shepard to do as he requested. Since Shepard was positioned facing the front of the capsule, the fluid collected behind the small of his back and eventually evaporated thanks to the pure oxygen environment on board. I always love this story because it really drives home how weird humans are in the context of spaceflight. Eventually, the long delays began to frustrate the pilot, and as the rescheduled launch time approached and more minor problems appeared, he called out, "Why don't you fix your little problem and light this candle?" with the last part going on to be a favorite quote of the early space program. At long last, at 9:34 a.m. on May 5th, 1961, the candle was indeed lit. The single Rocketdyne A7 engine at the base of the rocket roared to life, and Freedom 7 sprang off the launch pad with Shepard reporting, "Roger, liftoff, and the clock has started." For just under 2.5 minutes, Shepard endured the mounting forces imposed by the accelerating launch vehicle, eventually topping out at 6.3 Gs, or 6.3 times the force of gravity on Earth. The ascent was smoother than the pilot expected at first, though vibrations and buffeting began to increase after 45 seconds and became so severe as Freedom 7 passed through the period of maximum dynamic pressure, max Q, that Shepard said he was unable to read his dials. After max Q, Shepard reported much smoother conditions. All systems functioned as planned during ascent. The booster performed nearly flawlessly, the cabin pressure steadily decreased as the capsule rose, bottoming out at 5.5 psi as the proper valves closed, and there were no false positives causing an early abort. 10 seconds after booster cutoff, the now unnecessary escape tower jettisoned, and the spacecraft separated from the launch vehicle. Freedom 7 was flying in space. 30 seconds later, the automatic control system used a series of small thrusters positioned around the capsule to turn 180 degrees, with the heat shield now facing the direction of travel. The automatic controls were working exactly as planned. As soon as the booster engine shut down, both the pilot and his capsule became weightless. Weightlessness was the cause of much concern in the lead-up to human spaceflight. Many experts believed it would cause extreme disorientation, problems with cardiovascular and gastrointestinal systems, change the shape of the pilot's eyes, or make him too nauseated to perform mission tasks. While some of these concerns were later validated, weightlessness turned out to not only be largely benign, but pleasant. Astronaut Shepard later recalled that he wasn't even sure at first that he'd become weightless. He said to himself, "Well, okay, you've been weightless for a minute or two, and somebody is going to ask you what it feels like," which illustrates how comfortable he was with the microgravity environment. Given the short duration of the flight, Alan Shepard quickly began executing the series of test maneuvers designed to check the manual control system. It's interesting to note that Mercury actually had 4 different control modes, which involved 2 completely independent systems of thrusters. Shepard began maneuvering what was called the manual proportional system, which physically controlled valves to small thrusters using a series of mechanical linkages directly attached to his hand controller. The control systems of Project Mercury could easily take up a podcast of their own, however, so I'll save the extreme detail for a supplemental. Just quickly though, the main difference between the manual proportional mode and the fly-by-wire mode, which was the other mode under direct astronaut control, can best be described as a difference between analog and digital. With the manual proportional control mode, since the pilot was directly controlling the opening and closing of valves, he could smoothly vary the amount of thrust in a continuous fashion. Analog. With the fly-by-wire system, the controller caused the thrusters to fire at a preset low-power mode or high-power mode in short bursts. Digital. Shepard took control of the spacecraft one axis at a time. For those who are unfamiliar, the three axes are referred to as pitch, roll, and yaw. To use your head as an example, nodding up and down in a yes motion would be pitch. Shaking your head side to side in a no motion would be yaw. And tilting your head side to side, try touching your ear to your shoulder, is roll. Shepard started with pitch, placing the spacecraft in the proper attitude for re-entry, with the nose pitched down 34 degrees. While one axis was under manual control, the automatic system continued to keep the other two axes in line. Just as a quick side note, stuff like this always amazes me. At one level, Project Mercury was incredibly primitive, but here we have two completely different systems of thrusters, an automatic control system, and a human using manual control, controlling three different axes, all with no problem. It's amazing. Shepard next tested roll and yaw, and found that everything responded perfectly, with the only problem being that as he tried to use yaw, a part of his spacesuit bumped up against his parachute, requiring him to force his hand to achieve the desired motion. The next phase of the mission was to include observations of the Earth from space. When the astronauts first saw the Mercury capsules under construction, they immediately insisted that some sort of window was a mandatory feature. The engineers at McDonnell obliged, but not in time for the first piloted mission, so Shepard only had two small portholes which were placed at angles that made them awkward to use. Instead, he was to use the built-in periscope, which extended a lens outside the capsule and presented an image on the control panel. During the long delay before launch, Shepard had become irritated by sunlight entering the periscope and had activated a filter similar to sunglasses. Unfortunately, he neglected to remove the filter before launch and only noticed at this moment as he tried to begin observations. He made to retract the filter, but found that the motion caused the pressure gauge on his wrist to bump up against the abort handle. The escape tower was miles away at this point, and theoretically the handle wouldn't have done anything, but Shepard decided to play it safe and just live with the filter. So the whole time he was describing the wondrous sights he was seeing, it was through a dim gray filter. Improvisation always has been an important skill for astronauts. As Freedom 7 passed through the highest point of the trajectory, Shepard noticed the capsule had drifted to a pitch degree of only 20 or 25 degrees. At this point, the vehicle was under automatic control again. Shepard used the fly-by-wire control mode, where the hand controller essentially tells the automatic controls what thrusters to fire, as opposed to directly mechanically controlling them like the manual proportional mode, and began to correct the pitch problem. During the maneuver, the first of the three retro rockets fired, slowing the vehicle down. For this suborbital mission, the retro rockets were not strictly necessary, but they were critical for future missions, so were tested as if this were an orbital mission. The retro fire panel did not illuminate, but since Shepard had felt the, quote, comforting kick in the pants of the rockets firing and had seen pieces of the retro package flying past his window as they were jettisoned, he manually overrode the command. As the capsule fell along the re-entry path, Shepard took manual control via the fly-by-wire system. He was pleased to find that it felt very similar to the training systems on the ground, news which I'm sure his fellow astronauts also welcomed, as it meant their training would serve them well. As the atmosphere approached, the periscope retracted and the pilot placed his capsule back under automatic control. The Mercury capsules re-entered under a ballistic profile, which are considerably more punishing than the entry profiles flown by later missions. The crushing deceleration forces peaked at over 11 times the force of gravity on Earth. Re-entry passed without incident, other than some mild oscillations, which Shepard corrected manually in the fly-by-wire control mode. The drogue parachute deployed at 21,000 feet, and the main parachute deployed at 10,000 feet. In typical astronaut understatement, Shepard later said, "I was delighted to see it." As Freedom 7 floated gently toward the ocean, the heat shield dropped down and the cushioning landing bag deployed. One interesting thing to note here is that the two suborbital missions use beryllium heat-sink heat shields, instead of the ablative shields used on orbital missions. Early in the program, it was unclear if heat-sink or ablative shields would be the correct choice, so even though ablative shields were eventually chosen, heat-sink shields were available and suitable for the less demanding suborbital missions. Just in case I don't get back to it later, a heat-sink heat shield protects the capsule by absorbing heat and holding on to it. An ablative heat shield protects the capsule by essentially burning off small pieces, which fly away and carry the heat with it. Heat-sink shields were problematic for a number of reasons, and ablative shields were chosen for the rest of Project Mercury, Gemini, and Apollo. Only 15 minutes and 22 seconds after lifting off, Freedom 7 splashed down into the Atlantic Ocean. Helicopters quickly arrived and pulled the capsule out of the water enough for the pilot to exit via the main hatch instead of the more awkward nose cone egress route. 11 minutes after splashing down, both the capsule and Alan Shepard were back on the deck of the aircraft carrier USS Lake Champlain. The first American piloted spaceflight was complete. The short duration of the flight presents us with an interesting opportunity that won't be feasible for later episodes. If you take a look at the supplementals, which should be on the same podcast feed as the main episodes, you'll see that I have included the air-to-ground radio for the entire mission. It's pretty fascinating stuff, so I'd really recommend you give it a listen. Alan Shepard was an instant celebrity, even more than his Mercury 7 membership had already afforded him. While on board the Lake Champlain, he received an unexpected congratulatory phone call from President Kennedy. 3 days later, Kennedy awarded Shepard with NASA's Distinguished Service Medal in a ceremony at the White House. Large crowds appeared to cheer America's first spaceman down the streets of Washington, D.C. The public support was welcome to weary NASA engineers and important for the long-term goals of the agency. But the true value of the success of Freedom 7 was the wealth of data it had collected in piloted spaceflight. Humans could operate in the weightless environment of space. The vehicle could be controlled. Re-entry could be endured. The pilot could be kept alive in the void, and apparently it was possible to urinate in one's spacesuit with no consequences. In the aftermath of the successful flight, public support for spaceflight swelled. Aware of the impact on the world stage of the Soviets' early lead, President Kennedy sought a goal that was far enough in the future that the lead would be minimized. The path to the decision he reached was not straightforward or inevitable, and I will cover it in more detail in a future episode. But President Kennedy had decided to ask Congress to support a monumental undertaking. On May 25, 1961, only 20 days after America's first ever flight beyond Earth's atmosphere, President Kennedy delivered a speech to Congress which I will read in part. I am from Boston, but I'm not going to attempt the accent. Now is the time to take longer strides. Time for a great new American enterprise. Time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth. I believe we possess all the resources and talents necessary. But the facts of the matter are that we have never made the national decision or marshaled the national resources required for such leadership. We have never specified long-range goals on an urgent time schedule, or managed our resources and our time so as to ensure their fulfillment. Recognizing the head start obtained by the Soviets with their large rocket engines, and recognizing the likelihood that they will exploit this lead for some time to come in still more impressive successes, we nevertheless are required to make new efforts on our own. For while we cannot guarantee that we shall one day be first, we can guarantee that any failure to make this effort will make us last. We take an additional risk by making it in full view of the world, but as shown by the feat of astronaut Shepard, this very risk enhances our stature when we are successful. I believe this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind, or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish. The game was on. Thank you for listening to The Space Above Us. If you have any questions, comments, or feedback, please email me at jp@thespaceabove.us or via Twitter at the username @spaceaboveus. I'll see you in 2 weeks for NASA's next flight, Liberty Bell 7. Ad Astra, catch you on the next pass.